In term 2, the first chapter of physics is light, reflection and refraction. In our daily life, there are so many examples of reflection of light. For example, every morning when we start our daily activities or we start to get ready, we stand in front of a plane mirror and we get our image in the plane mirror. This is the example of reflection of light. The image formed by the plane mirror is due to only and only reflection. In this lecture, we learn about the properties of light. What do you mean by light? There are so many basic phenomena of light such as reflection and refraction. Here we learn about the mirrors and lenses and a little bit for the prism also. Basically, the light is a form of energy which gives us the sensation of seeing. Without light, it is not possible to view or to see any object in the nature. For example, there is a dark room. If we enter in the dark room, can you find any object in the room? Is it possible to see any object? No. Why? Because there is no light in the room. So there is no reflection take place from the object of the light and we are not able to see any object. Light is very necessary for the illumination of any object in the nature. Characteristics of light. The main characteristics of light are: number 1, the light waves are non-mechanical waves, that is, there is no medium required for the propagation of light waves. For example, the light waves emitting from the sun reaches on the earth by traveling a most part through the vacuum. Number 2, light waves travel through the vacuum with a speed of 299792458 meter per second, or approximately we call it as 3 into 10 raised to the power 8 meter per second. Light travels in the straight line. Here the formation of shadow shows the light travels in a straight line. Number 4, light can pass through transparent materials. This is the transparent material. So light can pass through transparent materials. This is the example. It cannot pass through opaque materials such as wood, steel, like that. This is the wood door. So light cannot pass out through the wood, but the small space is here. That means light can pass out through the air. Next, light can pass through translucent materials such as butter paper. Here light can pass some amount through the butter paper also. Light get reflected back from the polished surface. Such we say that from the mirror, the new utensils or any polished surface, light gets reflected back. Light suffers refraction as it passes from one medium to another medium which are transparent. These are the main characteristics of the light which we study here, and the phenomena of reflection and refraction based on these characteristics of light. Reflection of light. Do you know what is meant by reflection of light? We can define it in a very simple way. As we get up ready in every morning, we see our image in a plane mirror. That is only due to reflection. this is a highly polished surface, or we say it's a plane mirror. A line perpendicular to the mirror surface is known as normal. Here ON is normal. A ray of light AO incident at point O. After striking the polished surface, it bounces back in the same medium, that is OB. AO is called incident ray. OB is called reflected ray. That is, the ray which incident on the mirror is called incident ray, which reflects from the mirror is called reflected ray. The angle makes between the incident ray and normal is called angle of incidence. Here I is the angle of incidence. The angle makes between reflected ray and normal is called angle of reflection. Here R is angle of reflection. Now we discuss about the laws of reflection. There are two laws of reflection. One is, here the angle of incidence and the angle of reflection is always equal. That is, we say that angle I equals to angle R. The second law of reflection is the incident ray, reflected ray and normal all lie in the same plane. As you observe in the diagram, the incident ray AO, reflected ray OB and the normal ON all lie in the plane of the green board. So, we can say that they all lie in the same plane. These are the two laws of reflection. Let us take an example. A ray of light falls on a plane mirror at an angle of 60 degree from the mirror. Find the value of angle of incidence and angle of reflection. To completely understand the numerical, let us draw a diagram. This is a plane mirror. ON is the normal. AO and OB is the incident ray and reflected ray. According to the question, the ray makes an angle 60 degree with the mirror. that is this angle is 60 degree. We have to find an angle AON, this one. Here angle I equals to 90 degree minus 60 degree, that is 30 degree. Now according to the first law of reflection, angle of incidence is always equals to angle of reflection, that is so here we observe that the value of angle of incidence and angle of reflection both are equal to 30 degree. Let us differentiate between regular and irregular reflections. First we take regular reflection. There is a smooth and highly polished surface. There are three parallel rays which are incident on this highly polished surface. Then after reflection from this highly polished surface, the reflected rays are also parallel to each other. So in case of regular reflection, if any number of parallel rays incident on the surface, then after reflection the reflected rays are also parallel to each other. Let us take diffused reflection or irregular reflection. Here the surface is not completely smooth, it's a rough surface. XY be a rough surface, XY is the rough surface. Again there are three parallel rays incident on this rough surface. These are three parallel rays which are incident on the rough surface. After reflection, these three rays are not parallel to each other. They go here and there in the space, like so. This type of reflection is known as to be the diffused reflection. I'll give you an example. As we see our image in a plane mirror, that is only due to the reflection by a smooth and highly polished surface. If I am saying, as we read any newspaper, any notebook, why don't we see our image in the notebook? Because the surface of the notebook is not smooth and not polished. So that is the diffused reflection and we can't see our image. Here we discuss some activity which shows the properties of image formed by a plane mirror. The material required are the plane mirror with a stand here, an object, scale to measure the distance. Initially, we take a plane mirror in the vertical position like that and place an object in front of the plane mirror. Here you observe the image of this object in the plane mirror. The size of object and the size of image, that is same. Let us measure the size of object and the size of image. This is the scale. As we measure the height of object, that is 9 centimeter, and again we measure the distance or the height of image. This is again 9 centimeter. The distance of object from the plane mirror is same as that of the image. If we move the object away from the plane mirror, or we can say that if we increase the distance between the plane mirror and the object, the distance of the plane mirror and the image will also increase. From this activity, we conclude that the image formed by a plane mirror is same in size as that of object. Now we measure the distance of the object from the plane mirror. Here the distance of object from the plane mirror is 10 centimeter. The image again formed at the 10 centimeter from the plane mirror. So, as you see, the top of this object is blackened in color and the top of this image is also blackened in color. So, we conclude from this activity, the image formed by the plane mirror of any object is virtual. This is same size here and erect. Now we discuss about the lateral inversion. Here I write a letter P on a plain paper. Look at the mirror. What do you observe? You observe that the letter P is inverted. That means right side and the left side be inverted together. The lateral inversion means when the left side and right side reversal each other, this is known as to be the lateral inversion. So, this is a very important characteristic formed by the plane mirror, that the image always formed by the plane mirror is laterally inverted. That is why if we raise our left hand in front of the plane mirror, we observe that our right hand is raised in the image. So, students, do you get what is mean by the lateral inversion?
Yes, ma'am. The phenomenon due to which the image of an object turns through an angle of 180 degrees through a vertical axis, such that right side of the image appears as left or vice versa, is called lateral inversion.
Yes, exactly. Now, I will give you one more example for the lateral inversion. Generally, we observe the ambulance on the roads. The word ambulance written on the ambulance is inverted. The reason is, as we get the image in our rear view mirror, the image of this ambulance will be erect, so that we can easily read as ambulance and give the way to pass out the ambulance from the heavy traffic routes. Let us discuss how the image formed in front of the plane mirror. What are the laws we use here? There are the two cases. Let us discuss the two cases one by one. First is we take an object of point in size in front of a plane mirror and draw its image. This is the vertical plane mirror XY. O be the object of point size. Let us take one incident ray which falls normally on the plane mirror. Here angle of incidence is 0, so that angle of reflection is also 0. That is, the reflected ray bounces back on the same path, like that. Let us take one more ray OB, which is incident on the plane mirror. By making any angle of incidence I. Reflects back at an angle of reflection R. So BC is the reflected ray of OB. Here we observe that the first reflected ray, that is AO, and the second reflected ray BC never intersect each other on the same side of the object. So we produce these two rays in the back of the mirror. These two rays, after producing in the back of the mirror, intersect at point O dash. So O dash is the image of point object O. The nature of O dash is virtual, erect, the same size of the object, and behind the plane mirror. Let us take case 2 for extended object. This is again a plane mirror XY which placed vertically. An extended object AB is placed in front of the plane mirror. Let us consider that A be the point size, and we draw the image of point A, and then we draw the image of point B. Let us start with point A. There is a ray AN which is incident normally on the plane mirror. After reflection, bounces back on the same path. We take one more ray say AM, which is incident at any value of angle of incidence. At the same value of angle of reflection, it reflects back. Like that. Here again we observe that these two reflected rays can never intersect on the same side of the object. So we produce them in the back of the plane mirror. These two reflected rays intersect at point A dash. So A dash be the image of point A behind the mirror. In the same case, consider as point B. the reflected ray bounces back on the same path. For another incident ray at any value of angle of incidence, QR be the reflected ray. Here QR and PB never intersect on the same side of the object. Again we produce them in the back of the mirror. They both intersect at point B dash. That is, B dash is the image of point B. Now join A dash, B dash. So A dash, B dash be the reflected image of extended object AB. Here we observe that A dash, B dash is of the same size of AB. It is erect, virtual, and as at the same distance as object behind the mirror. Let us start with mirrors. There are two types of mirror, plane mirror and spherical mirror. Again, a spherical mirror is a highly polished curved surface. There are two types of spherical mirrors. One is concave mirror, a mirror whose inner hollow surface is the reflecting surface is called concave mirror. It is also called converging mirror because after reflection it converts the rays of light. Number 2, convex mirror, a mirror whose outer bulging surface is the reflecting surface is known as convex mirror. It is also called diverging mirror because after reflection the rays of light which are coming from infinity, they are diverging out from a point. Let us start with the terminology used in the case of mirrors. Here, to define the terminology, first we imagine a hollow sphere in which we take two of its part. One is this one part in which the outer part is polished and inner part is considered as to be the reflecting surface. The other part here, the inner part is polished and outer bulging surface is the reflecting surface. First we take aperture. Aperture means the part of the mirror which is responsible for the reflection of light. Here in the case of concave mirror, L dash, this is the reflecting part, so it is known as to be the aperture of concave mirror. Here M dash, which is the reflecting surface of the convex mirror, is known as to be the aperture. Next is pole. The middle point of the mirror, this one P here and P here, the pole of concave mirror and the pole of convex mirror. Third one is center of curvature. Center of curvature means the center of this hollow sphere of which the mirror is the part is known as to be the center of curvature. C indicates the center of curvature. Now principal axis, a line which passing from P and C, this one is known as to be the principal axis. In the same case for the convex mirror, a line passing from pole and center of curvature is known as principal axis. Now focus, F, a point on the principal axis from which after reflection the rays of light meet, so it is known as to be the focus point of concave mirror, and the focus of convex mirror defined as where the rays of light after reflection appears to meet. This is known as to be the focus of convex mirror. This focus is the midpoint of P and C. That is, in the same case for the concave mirror, F is the focus, which is the midpoint of P and C. Radius of curvature. The distance between the P and C, or the radius of this hollow sphere, is known as to be the radius of curvature for concave mirror and for convex mirror. Focal length. The distance between pole and focus is known as focal length. We are discussing the focus and focal length of mirror. Here, the focus and focal length of a concave mirror. There is a concave mirror. This is the principal axis of the concave mirror. P is the pole. A parallel beam of light coming towards the reflecting surface of concave mirror reflects and actually meet at a point, this point F. This is known as the focus of concave mirror. The distance between focus and pole of the concave mirror is known as focal length of the concave mirror. Focus and focal length of a convex mirror. Take a convex mirror, draw the principal axis P with the pole of convex mirror, a parallel beam of light coming towards the reflecting surface of convex mirror. They diverge from the point and appear to meet at point F, or they appear to diverge from point F. The point F is the focus of convex mirror. The distance between focus and pole is known as to be the focal length of convex mirror. Real image. When the two reflected rays actually meet at a point, a real image is formed. Here, a concave mirror, principal axis CF, the two rays coming after reflection, they actually meet at this point, a real image is formed. In the same case of a lens, when the two rays which are refracted from the lens actually meet at a point, a real image is formed. Remember one important thing, in case of mirror, the real image is formed on the same side of the object, but in the case of lens, a real image is formed on the other side of the object. Virtual image. When two reflected rays appear to meet at a point, a virtual image is formed. Here, a concave mirror, center of curvature, focus, principal axis, an object is placed, two rays coming out from object. After reflection, they appear to meet behind the mirror, a virtual image is formed. In the same case for the lens, when the two rays appear to meet at a point after refraction, a virtual image is formed. Again, remember very important thing, in the case of lenses, a virtual image is formed on the same side of object, and in the case of mirrors, a virtual image is formed on the other side of the objects. Let us compare the real and virtual image. First we consider in case of mirrors. Here, there is a concave mirror, an object is placed here between C and F, the image formed on the same side of the mirror as that of the object, then the image is real. In the case 2, the concave mirror is placed, object is placed under focus of a concave mirror, the two rays appears to meet behind the mirror so that the image is formed on the other side of the mirror as that of object. This image is to be virtual. As similarly, in the case of lenses, the real image is formed on the other side of lens and the virtual image is formed on the same side of the lens. Let us take the rules to draw the ray diagram by the spherical mirrors. There are 4 rules how to draw the ray diagrams with the spherical mirrors. Let us take one by one. The first one is if a ray which is coming parallel to the principal axis incident on a spherical mirror like that, after reflection it always go from the focus of the mirror in case of concave mirror. In case of convex mirror, the ray after reflection appear to diverge from the principal focus of the convex mirror. Rule 2 is the same rule as above, but in vice versa condition. That is, if a ray coming from the focus of any spherical mirror, then after reflection it becomes parallel to the principal axis, like this. The ray incident through the focus, after reflection it becomes parallel to the principal axis. Case 3 is if any ray incident on the spherical mirror passing through the center of curvature, it bounces back on the same path. Like this. Ray incident and passing through center of curvature bounces back on the same path, that is in the just 180-degree direction oppositely. Case 4. If any ray of light incident on the pole of spherical mirror at an angle of incidence I, it reflects back at an angle of reflection R, and according to laws of reflection, angle I equals to angle R. Here the most important thing, the principal axis is always normal at point pole P. So, PC is the normal. The incident ray AP makes an angle of incidence I. The reflected ray BP makes an angle of reflection R, and according to laws of reflection, angle I equals to angle R. That is the same rule for the convex mirror also. Let us start to learn about the sign convention for the mirrors. Consider there is a Cartesian plane and origin be considered as the pole of the mirror. The distances moved in the right of the pole are taken as to be the positive sign, and the distances moved in the left of the pole are considered to be the negative sign. Similarly, the distances considered in the upward direction from the axis or the principal axis or the x-axis are considered to be positive, and the distances moved in the downward direction are considered to be negative. Let us consider a concave mirror and to learn about the sign convention for the concave mirror. Here, there is a Cartesian plane in which the axis x, x dash and y, y dash. Now, a concave mirror MN be placed such that the origin, which is the intersection point of x dash and y dash, be coincide at the pole of the mirror, this point P. Here, an object AB is placed vertically upwards on x dash. Light is coming from left to right. The distance taken PB, which is in the left side of the pole, or the distance against the incident light, is considered to be negative. Similarly, if we say that the image of object AB is formed as A dash B dash, it is given as negative sign because it is in the left of the pole and the distance against the incident light. If there is any object or any image be formed at here, it is taken as to be positive sign because it is in the right of the pole and the distance along the incident light. Here, BA be the object which is vertically upwards, so the distance is taken as positive, and the image B dash A dash, it is in the negative direction of y axis or downward direction, so it is considered as negative sign. Let us discuss the ray diagrams formed by concave mirror. Here, the ray diagram of concave mirror when an object is placed at infinity. Take a concave mirror, draw a principal axis, mark a point P as pole, F as focus and C as center of curvature. Remember, F is midpoint of PC. A parallel beam of light coming from infinity. After reflection from the surface, they meet at focus. It indicates the final image is formed at focus. The nature of image is real, inverted and highly diminished, or we can say that the size of image is exactly the point size. Let us discuss the ray diagram of concave mirror when object is placed between F and C. Take a concave mirror, draw the principal axis, mark point pole P, F as focus and C as center of curvature. An object BA is placed between C and F. The ray is coming out. After reflection, they actually meet at the point A dash, and the final image B dash A dash is formed. The final image B dash A dash is formed beyond center of curvature. The nature of image is inverted, real and enlarged. The ray diagram of concave mirror when object is between focus and pole of mirror. Take a concave mirror, mark as a principal axis, take a point P as pole of the mirror, F is the focus of the concave mirror and C be the center of curvature. An object BA is placed between F and P. The two rays after reflection diverge. If we join them in back, or they appear to meet at point A dash behind the mirror, so that the final image B dash A dash is formed. The nature of image is virtual. The image size is more than the object size, that is enlarged, and the image formed behind the mirror. The final image is virtual, enlarged and behind the mirror. Now we discuss the image formation by convex mirror. Here the ray diagram for convex mirror when object placed at infinity. Take a convex mirror, principal axis, pole, focus C, parallel beam of light coming from infinity. After reflection they diverge outside and they appears to meet at point F. It indicates that the final image is formed at F. The nature of image is highly diminished and virtual and erect. We can say that the size of image is point in nature. Ray diagram of convex mirror when object placed between pole and infinity anywhere. Take a convex mirror, principal axis, pole, focus. An object BA is placed. The two rays coming out after reflection, they diverge and appear to meet behind the mirror at point A dash. That indicates the final image is B dash A dash. The nature of image is virtual, diminished, erect, and the final image formed behind the mirror between pole and focus. Image formation by concave mirror. First case is when object placed at infinity. Here there is a concave mirror, the rays of light coming from infinity. Now where the image is formed? Image formed at focus of the concave mirror. The size of image is highly diminished. The nature of image is real and inverted. But if the image is in point size, we can't distinguish about inverted and erect images. Case 2, when object placed beyond the center of curvature. Here object BA placed beyond center of curvature of concave mirror. The rays coming and after refraction they meet at point A dash. So the image of object BA is B dash A dash. The B dash A dash is diminished and real and inverted image of the object. Case 3, when object placed at center of curvature C. Here object BA is placed at center of curvature C. After reflection, the rays met at point A dash. That is, image formed is B dash A dash. Where the image is formed? Image again formed at C. That is, the image and object both formed at the same point. Image is real and inverted, and the size of image is same as that the size of object. Next case, when object placed between focus and center of curvature. This is the object placed between C and F. After reflection, the image formed at B dash, that is beyond C or center of curvature. The nature of image is real, inverted, and the size is enlarged. The next case, when object placed at focus. An object placed at the focus, then after reflection, the image formed is real and inverted. After reflection, the rays are parallel so that they meet at a very high distance, that is, the size of image is highly enlarged. Next, when object placed between focus and the pole of the mirror. Object is placed between F and P. The image formed behind the mirror at point B dash, and it is virtual, erect and enlarged image. This is the only case in the concave mirror where the image is virtual in nature and formed behind the mirror. Image formation by convex mirror. In case of convex mirror, because it is a diverging mirror, the image is formed behind the mirror. So, in case of convex mirror, always the image formed virtual in nature. Case 1, when object placed at infinity. There is any object placed at infinity, rays coming parallel to principal axis. After reflection, the rays meet at the focus of the mirror, that is behind the mirror. Thus, the nature of image is virtual, erect and highly diminished, or we can say that the image is point in size. Next case, when object placed between infinity and pole. The object placed between infinity and pole, after reflection, the image formed again behind the mirror, and the nature is virtual, erect and the size is diminished. And the image formed between focus and the pole of the convex mirror when any object placed between infinity and pole of the convex mirror. Let us discuss the relation between the focal length and radius of curvature of a spherical mirror. This is the concave mirror. PF be the focal length and PC be the radius of curvature. Always remember that F is the midpoint of PC. That's why focal length is always half of the radius of curvature. Remember a very important point about the sign conventions. Here you observe that the point F or the focal length and the point C or the radius of curvature both are in the left of the pole of the mirror. That's why focal length and radius of curvature for concave mirror is always negative. Let us discuss again the convex mirror. the relation between focal length and radius of curvature for the convex mirror is same as that of concave mirror. Now about the sign conventions, here you observe that F and C are in the right direction of the pole. That's why F and C, or F focal length and the radius of curvature for the convex mirror, are positive. Students, do you know what about the focal length of a plane mirror?
Ma'am, as the plane mirror is assumed to be the part of the spherical mirror of infinite radius of curvature, and as the radius of curvature is infinite, its focal length is infinity.
Yeah, because we consider that the plane mirror is a part of a very huge size spherical mirror, that is the radius of curvature is infinity, and similarly focal length is equals to half of infinity, that is again infinity. Let us take an example. The radius of curvature of a concave mirror is 30 centimeter. Find its focal length. As we know that the center of curvature of the concave mirror is on the left side of the pole, so that the radius of curvature of the concave mirror is always negative. We know the formula or the relation between F and R. F equals to R by 2, thus focal length of the concave mirror is negative 15 centimeter. Here we take a modification in the question, students. Rather than we take a concave mirror, if we take convex mirror here, then tell me what's the value for radius of curvature?
Ma'am, I think negative sign will not be there.
Yeah, sure. In the case of convex mirror, the center of curvature is on the right side of the pole. That's why the radius of curvature is positive nature, and hence the focal length also is positive in nature. Now we discuss a very important relation, that is mirror formula. What exactly the mirror formula is? Mirror formula is the relation among the distance of object from the pole, distance of image from the pole, and the focal length of the mirror. Mathematically, we write it as the reciprocal of focal length of the mirror is equal to the reciprocal of distance of object from the pole plus the reciprocal of distance of image from the pole. As we know that the focal length is denoted by letter F, so we write it as 1 by F. Distance of object from the pole denoted by U, and the distance of image from the pole is denoted by letter V. So this relation is known as to the mirror formula. Remember one very important thing in case of mirror formula, as we apply a mirror formula in any of the questions, keep the sign conventions in your mind. Let us take a numerical. At what distance from a convex mirror of focal length 30 cm should an object be placed so that its image is formed at 20 cm from the mirror at right side? First we analyze the question here. Here we find out the distance of object from the mirror, that is, we find the value of u. U is unknown here. Next is the focal length is 30 cm and the mirror is convex in nature, that is, the focal length is positive in nature. The distance of image from the mirror is 20 and is on the right side of the mirror, that is, V is also positive. Now we use the mirror formula. Plug the values of F, U and V. We have to find the value of U. Here. Now take the LCM of 30 and 20, sorry. That is, the value of U is minus 60. Negative signs show that the object should be placed at a distance of 60 cm in front of the mirror. Let us discuss about the magnification produced by the spherical mirror. What exactly the magnification is? By the help of magnification, we compare the size of the object and the image. So, it is defined as the ratio of size of image to the size of object. Small m indicates for magnification, I indicates for size of image and O indicates for size of object. If we draw any ray diagram in any of the case for any spherical mirror, we observe that the ratio I by O becomes minus V by U. So, this is the magnification produced by the spherical mirror. Let us take some cases. If the value of m is less than 1, then the image formed is diminished. If the value of m is greater than 1, the image formed is enlarged or magnified. If the value of m is exactly equal to 1, then image is of same size as that of object. There are two more cases. If magnification is negative, it means the image is real and inverted. If magnification is positive, the image formed is virtual and erect. Let us take one more numerical on the basis of magnification produced by the spherical mirror. Here, an object of length 2.5 centimeter is placed at 1.5 f distance from a concave mirror. Find the length of the image. Is the image erect or inverted? Let us first analyze the question. The focal length of the concave mirror f is, say, small f, which is always negative. The distance of object is given, which is equals to 1.5 f, and it is negative because the object placed on the left side of the pole. The height of object O is given (2.5 centimeter). We have to find out the length of image, that is I, and the nature. Let us draw a rough ray diagram. This is the diagram. AB be the object placed perpendicularly to the principal axis at a distance of 1.5 f from the mirror. Now we use mirror formula. So we calculate the value of 1 by V, that is equals to minus 3f. It is in the form of again focal length. Now we take the formula for the magnification. M equals to I by O, which is again equals to minus V by U. We find the value of I. O given as 2.5. O has positive sign because the object placed upwards from the principal axis. Minus V is minus 3f. U is minus 1.5f. So I becomes minus 5 centimeter. Because I is negative in sign, that is image formed downwards from the principal axis. So the image formed is inverted. If it is inverted, magnification is also negative, that is image formed is real in nature also. That is the final image formed of size minus 5 centimeter, which is inverted and real in nature. Let us perform an activity which shows the bending of ray of light as it passes from one medium to another. Material required: an empty glass, a glass half filled with water, and a stick. As we dip the stick in empty glass, the stick appears to be the straight. If we place the stick in the glass containing some water, we observe that the stick appears to be bent at a particular point. This is due to the refraction through the water in the glass. Let us take another topic, refraction. To understand the topic of refraction, first we take two mediums which are transparent, held one on each other like that. There are two different mediums, medium A and medium B, which are separating by an interface X, Y. These are totally transparent mediums. For example, we can say that medium A be the air and medium B be the glass. There is a normal to the interface of the two mediums NOM. So, the phenomena of bending of ray of light as it passes from one transparent medium to another is known as refraction. Here we take an incident ray AO which is incident in medium A at an angle of incidence I. As this ray enters into the medium B, the path of the ray will deviate. This deviation of the ray or in the path of the ray, it is known as to be the refraction. The original path is like that and OB be the refracted ray, that is ray OB is deviated at any angle. This is due to the change in the speed of light from one medium to another. That is, refraction only take place when there is change in the speed of light as the ray enters from one medium to another medium.
Ma'am, in this case, angle of I and angle of R both are equal?
Never. If angle I and angle R are equal, that means there is no any change in the rays of the path of the rays of light, or we can say that there is no any change in the speed of light in both of the mediums. Angle I and angle R are never to be the equal. May be possible angle I is greater than R or angle I is less than R. It depends on different situations. After that, we will take these two different situations. Let us take two different cases when the ray of light travels from rarer to denser medium and denser to rarer. First we take rarer to denser. This is the interface which separates the two medium A and medium B, which are of different optical density. NOM is a normal, ray AO is incident on the interface at point O at an angle of incidence I. When the ray of light moves from rarer medium to denser medium, A be the rarer medium and B be the denser medium, it bends towards the normal, that is the ray OB is refracted ray. In this situation, the value of angle I is greater than value of angle R. Now the case 2, when the ray of light passes from denser to rarer medium. This is the interface let this medium be, which is denser, and this is medium, rarer. NOM be the normal, ray AO incident at point O at an angle of incidence I. Then after refraction it bends away from the normal like this. In this situation, the value of angle I is less than value of angle R. Let us discuss about the laws of refraction. There are two laws of refraction. Now first we discuss about the first law. Let us draw some diagram. For the two pair of mediums, the ratio of sine of angle of incidence to the sine of angle of refraction is always constant. For example, if the medium B is glass and medium A is air, whenever we take always such glass slab and air, what are the values of I and R? The ratio of sin I and sin R always remains constant. Second law, the incident ray AO, the refracted ray OB and the normal NOM all lie in the same plane. Here you observe that all the rays, that is AO, OB and the normal NOM, all in the lie of the plane of the board, that is they all lie in the same plane. These are the two laws of refraction. Now we move on the very important topic based on refraction, that is refractive index. What exactly the refractive index? The refractive index is basically depends on the optical density of the medium. Here absolute refractive index is the ratio of speed of light in vacuum to the speed of light in that medium. That is refractive index denoted by a Greek symbol mu, C divided by V, where C denotes the speed of light in vacuum, that's always equals to three times 10 to the power 8 meter per second, and V is the speed of light in that medium whose absolute refractive index is to be calculated. Always we know that the velocity of light in vacuum is maximum, that is the ratio C by V always greater than 1. That is the refractive index of the medium is always greater than 1 if we take the absolute one. Let us discuss the refractive index of the two mediums with respect to each other. This is medium 1. This is medium 2. If we say that 1 mu 2, it reads as refractive index of medium 2 with respect to medium 1. That is 1 mu 2 is written as speed of light in medium 1 divided by speed of light in medium 2. If we reverse the condition, we write it as 2 mu 1. This relation is also inversible. That is speed of light in medium 2 divided by speed of light in medium 1. We write it as speed of light in medium 2 divided by speed of light in medium 1. Students, tell me one thing. What is the unit of refractive index?
Ma'am, it is unitless.
Yeah. Why? Because the ratio of the same quantities, the ratio of speeds, that is on the numerator the unit is meter per second, the denominator the unit is again meter per second, so cancels out each other. There is no unit of refractive index. Let us take an example on the behalf of refractive index to understand the topic completely. The wavelength of light in air is 7800 angstrom. What is the wavelength of this light in a medium whose refractive index is 4/3? We know that the refractive index depends on the wavelength of light, that is wavelength in air, wavelength in medium. Here the refractive index is 4/3, wavelength in air is 7800. We have to find out wavelength in medium. So wavelength in medium, that is equals to 5850 angstrom. Here we can say that the refractive index of any medium is the characteristic property of the medium, and the refractive index depends on the nature of the material of the medium and the color or the wavelength of the light used. Let us take one more very important numerical on the behalf of refractive index. Light enters from water into a glass plate and the refractive index of glass plate is 9/8 with respect to water. The speed of light in vacuum and glass is 3 into 10 to the power 8 meter per second and 2 into 10 to the power 8 meter per second respectively. Find refractive index of glass, refractive index of water and the speed of light in water. First we analyze the question. Here the refractive index of glass with respect to water is given, that is W mu G is 9/8 is given. Speed of light in vacuum 3 into 10 to the power 8 and the speed of light in water is 2 into 10 to the power 8 meter per second. This is the speed of light in vacuum, this is the speed of light in glass. Now take part A. the refractive index of glass. Refractive index of glass is equals to speed of light in vacuum to the speed of light in glass. 3 into 10 raised to the power 8, 2 into 10 to the power 8, that is 3 by 2. That is, the refractive index of glass is 3 by 2. Now case B. Refractive index of water. Here we know that W mu G, that is refractive index of glass with respect to water, is refractive index of glass with respect to vacuum or air to the refractive index of water with respect to air. If we want to find the value of A mu W, that is A mu G divided by W mu G, which is equals to A mu G from the A part 3 by 2 and W mu G is given as 9 by 8. The answer is 4 by 3. Now the case C. The speed of light in water. A mu W means speed of light in air to the speed of light in water. So the speed of light in water equals to 3 into 10 to the power 8 divided by refractive index of water, which is 4 by 3, that is 2.25 10 to the power 8 meter per second. So the refractive index of glass is 3 by 2, the refractive index of water 4 by 3, and in the part C the speed of light in water is 2.25 10 to the power 8 meter per second. Here we show that how the spoon behaves like a concave and convex mirror. Take a stainless steel spoon, and this part, which is inner part, that is worked as a concave mirror, and the outer bulging part acts as a convex mirror. You take the spoon in your hand and observe your image in the spoon on the concave side. You observe that the image is inverted. If we invert the spoon so that the convex part is in front of you, you get that the erect image is in front of you in the spoon. Thus, the spoon behaves concave mirror as well as convex mirror. Lenses. It is a transparent medium bounded by two surfaces. There are two types of lenses: convex lens and concave lens. Let us learn about the terminology of lenses. First, we take convex lens. Here, there is a convex lens. Aperture. The part of the lens which is responsible for the refraction, that is L dash, is known as aperture of convex lens. Optical center. The midpoint of the lens is known as optical center. Principal axis. A line passing through the optical center and perpendicular to both of the faces of the lens is known as principal axis. A convex lens is also called as converging lens, because if the rays of light coming from the left side of the lens, after refraction they converge at the principal axis on the right side. That's why it's known as convex lens as convergent lens. Next is concave lens. Here is a concave lens. M dash is known as to be the aperture of concave lens. This is the responsible part for the refraction. O be the optical center of the concave lens, and this line be the principal axis. Principal axis is a line which passing through optical center and the two refracting surfaces, and it's always perpendicular from two refracting surfaces. A concave lens is known as diverging lens. If the rays of light coming from the left side of the lens, then after refraction they appears to come from one point and diverge. So it is known as to be the diverging lens. Let us take an activity in which we show about how the refraction take place from concave lens and convex lens. This is the light source, this is the cardboard box, and we make a slit so that we get an image here. This is the concave lens and this is convex lens. Now the light source, cardboard box in which the image here form. First we take concave lens placed in front of the light, we get the pattern of slit which is diverging in nature, which indicates the concave lens form a diverged image of the object. Again we place convex lens so that the rays converge and we get a single image of the slit, which indicates its work as a convergent lens. Now we take both the two lenses, combine, and we got the same image. There is no any divergence and convergence here, that is the both lenses nullify the effect of divergence and convergence of each other, and the image remains same as that there is no lens or lens combination here. Let us discuss the focus and focal length of convex lens. Focus and focal length of a convex lens. Take a convex lens, this is the principal axis, optical center O. A beam of parallel rays of light coming after refraction, they meet at point F2. This point F2 is the main focus of the convex lens. The distance between the optical center and F2 is known as to be the focal length of convex lens. Let us discuss the focus and focal length of concave lens. Focus and focal length of a concave lens. Take a concave lens, this is the principal axis, optical center, parallel rays coming out, after refraction they diverge or they appears to come from a point F1. So F1 is the focus of concave lens. The distance between O and F1 is the focal length of concave lens. F1 is also called the virtual focus of the concave lens. Now we discuss about the rules to draw the ray diagram in case of lenses. There are three rules for both of the lenses. First one is if any of the ray coming parallel to the principal axis in front of a convex lens, then after refraction from the convex lens it passes from the focus. In case of concave lens, it appears to come out from the focus after refraction. The rule 2 is the inverse of the same rule. if any of the ray coming through the focus of the convex lens, then after refraction it becomes parallel to the principal axis. Case 3. If a ray comes through the optical center, it becomes undeviated after refraction in both of the lenses. So, these are the rules to draw the ray diagrams with the help of lenses. Sign convention of lenses. As like in the mirrors, the sign convention of the lens, they are very similar to each other. Consider that there is a Cartesian plane and origin be considered as the optical center of the lens. Now, the distances moved in the right direction or in the upward direction of the optical center are given as positive sign, and the distances moved in the left direction or downward direction from the optical center are given as negative sign. Here we discuss about a convex lens. This is the convex lens and this is the x-axis, y dash be the Cartesian plane. O be the optical center or the origin, they both coincide. Object be placed BA in the left direction and the image of object BA formed B dash A dash. The light is coming from left to right. So, the distance OB is taken as negative because in the left of the optical center, and the distance moved again the direction of incident light. The distance OB dash is also considered to be negative because it is in the left of optical center and again the distance against incident light. The distance in the upward direction AB dash taken positive and in the downward direction is taken as negative. If any object or image be placed on the right direction of this optical center, it is taken as positive because it is in the right direction of optical center and the distance move along the incident light. Let us discuss the image formation by the convex lens when the object placed at various positions. Here we discuss about the ray diagram of a convex lens when object placed at infinity. There is a convex lens, principal axis, optical center focus, the rays coming parallel to the principal axis. After refraction through the lens, they meet at focus F. That means the image is formed at F. The nature of image is highly diminished, real and inverted. We can also say that the size of image is point. Next is ray diagram of convex lens when object placed at 2F. Convex lens, a principal axis, optical center, focus and 2F on both the sides. An object AB placed, the two rays after refraction they meet again at 2F, final image A dash B dash is formed. The nature of image is real and inverted and the size of image is exactly same as the size of object. Here the ray diagram of convex lens when object is between F and O. Convex lens, draw principal axis, point to optical center, focus, an object AB, the two rays coming out and after refraction they diverge or they appear to meet behind the object and at B dash the final image A dash B dash is formed. The nature of image is enlarged, virtual and erect and on the same side of the lens. Now we discuss about the image formation by concave lens. Ray diagram of concave lens when an object placed at infinity. There is a concave lens, principal axis, F2F and O. The rays coming from the infinity, they diverge after refraction and appears to meet at focus. That indicates the final image formed at focus F. The nature of image is virtual, erect and highly diminished, or we can say that the image formed is point in size. Ray diagram of concave lens when an object is between infinity and optical center. There is a concave lens, mark the principal axis, F, O and F. Object AB is placed here. The rays coming out from the object, after refraction they diverge or appear to meet at B dash, that is final image A dash, B dash is formed. The nature of image is virtual, erect and diminished. The final image A dash, B dash is formed between F and O. Image formation by convex lens. First case, when object placed at infinity. There is a convex lens. The rays are coming parallel from infinity. After refraction, they meet at the focus here. The nature of image is real, inverted and highly diminished, or we say that point in size. Next case, when object placed beyond 2F. Object placed beyond 2F, after refraction the image formed between F and 2F. The nature of image is diminished, real and inverted. Next case, when object placed at 2F. When object placed at 2F, after refraction the rays meet at point again 2F, image formed at 2F, the size is same, nature is real and inverted. Next case, when object placed between F and 2F. Here the object placed AB, after refraction the image formed beyond 2F. What about the nature? The nature is real, inverted and enlarged. The next case, when object placed at focus F. Here the object placed at F, after refraction the two rays of light are just parallel to each other. That means they meet at infinity. That is the final image formed at infinity. The nature is real and inverted. In the last case, which is the very important case for the convex lens, when the object placed between focus and optical center. After refraction, we observe that the rays meet again behind the object, that is on the same side of the object, so that the image is erect, enlarged and virtual. This is the only case in the convex lens where the object placed between the focus and the optical center and the final image is virtual in nature. Image formation by concave lens. In the case of concave lens, always the image formed is virtual in nature because the lens is diverging in nature. We take a case where the object placed at infinity. When the object placed at infinity, the rays are coming parallel to the principal axis and after refraction they appear to meet at the focus of the lens. That's why the image is virtual, erect and highly diminished, or we can say that the size of image is point size. Next case, when object placed between infinity and optical center anywhere. Here the object is AB. Object AB is placed in front of concave lens. After refraction, the rays appears to meet at point B dash, that is the final image is formed A dash B dash, which is in between F and O. The nature of image is virtual, erect and diminished. Now we discuss about the lens formula. It is the relation among the focal length of the lens, the distance of the object from the optical center and the distance of image from the optical center. The relation is focal length denoted by F, distance of image denoted by V and distance of object denoted by U. This relation is known as the lens formula. Students, remember one thing, in case of mirror formula, there is a positive sign between 1 by V and 1 by U, but in case of lens, the sign is negative. Next is magnification. As in the same case of mirrors, the magnification produced by the lenses is the ratio of size of image to the size of object. From all of the ray diagrams as we discussed earlier, the ratio of size of image to the size of object becomes to be the distance of image to the distance of object, that is V by U. Now there are 5 cases for the magnification. If M is less than 1, image is diminished. Case 2, if M is greater than 1, the image is enlarged or magnified. Case 3, if magnification equals to 1, the image is of same size. Case 4, if M is negative, the image formed is real and inverted. And the last case, if magnification is positive, the nature of image is virtual and erect. In the case of magnification, we can say that magnification is the factor which decides the nature of image formed by the lens or formed by mirrors. Remember one more thing, the magnification produced by the mirrors is minus V by U here, but in the case of lenses, the magnification produced is only V by U. Let us take a numerical on the behalf of magnification. Find the size, nature and position of image formed when an object of size 2 cm is placed at a distance of 20 cm from the convex lens of focal length 10 cm. First we analyze what is given and what we have to find out. Here the size of object is given O 2 cm, distance of object from the lens U minus 20 because object is placed in the left side of the optical center of the lens. We have to find out the position. Focal length is also given, that is 10 cm. The focal length of convex lens is always positive because it is in the right side of the optical center. Let us draw a rough diagram to understand completely the question. This is the optical center. This is focus. Object is placed AB here. First we use lens formula. The position of image is 20 cm. It is positive. That means the image formed on the right side of the optical center. Magnification is I by O, V by U. Here we have to find out the value of I. O is given 2 cm, V is 20 and U is again minus 20. I becomes minus 2 cm. I is of negative sign, that is image formed inverted. On the other side, that is real, and the size of image 2 cm, which is same as that of object, so that the image formed at 20 cm on the right side of the lens, which is real and inverted in nature, and the size of image is same as that of the object. Now we discuss one more question about concave lens. A 6 cm high object is placed at a distance of 12 cm from a concave lens of focal length 12 cm. Find the size of the image. First we find out what is given in the question and what we have to find out. A 6 cm high object means O is given 6 cm. Object is always placed on the upside of principal axis, so O is positive. Distance of object is given and always it is putting on the left side, so it is negative. Focal length of concave lens is always negative, that is F equals to minus 12 cm. We have to find out I. Let us analyze some ray diagram. This be the concave lens, this be the focus, and object is placed here again. This is optical center O. First we use the lens formula. Plug the values of f. We have to find out v, and the value of u is -12. The value of v is -6. Magnification is I by u, that is v by u. We have to find out the value of I. O is given 6, v is -6 and u is -12, which indicates I equals to 3 centimeter. As we observe that v is negative, that is on the left side, which indicates the image formed is virtual. I is positive in nature, that is image is erect, and the size of image is 3 centimeter. Finally, we can say that a virtual image is formed of size 3 centimeter, which is erect in nature on the same side of the object. Now we discuss about the power of a lens. What exactly the power of lens? What the lens is doing? Convex lens is converging the rays and concave lens is diverging the rays. That means the ability of any lens to converge or to diverge the rays of light is known as power of a lens. Mathematically, the power of lens is measured as the reciprocal of focal length of the lens. Remember that here focal length should be measured in meter. The unit of power of lens is diopter, that is capital D. As we know that for convex lens, focal length is positive, thus power is also positive. In case of concave lens, focal length is negative in nature, that's why power is also negative in nature. As we go to the eye specialist and check our eyes, eye specialist give a number to us. What is that number? That number is exactly the power of the lens which you have to use. Whenever the power given by the doctor is negative, that means you have to use concave lens, and the power is positive, you have to use convex lens. Now we take an example on the behalf of power of lens. What is the power of convex lens of focal length 40 centimeter? Here the lens is convex in nature, so that the focal length is positive. We know the formula, power equals to 1 divided by focal length when focal length measures in meter, or 100 divided by focal length when focal length measures in centimeter. So, power equals to 100 divided by 40, (2.5 diopter). Thus, the power of this convex lens whose focal length is 40 centimeter is 2.5 diopter. Let us take another example for the power. Find the focal length of concave lens of power -1 diopter. Here power is given -1 diopter. By using the relation between power and focal length, P equals to 100 by F, F equals to 100 by power, that is -1, then the focal length of this concave lens is -100 centimeter. Thus we say that the focal length of this concave lens is -100 centimeter. Now find out the focal length of combination of two or more lenses which are placed in contact with each other. There are two lenses. Here we show that only the two convex lens. They may be both convex, they may be both concave, or one concave, one convex. Remember that the Sine convention used for focal length. The focal length of first lens is f1 and the focal length of the second lens is f2. If the two lenses are placed in contact to each other, they behave like a single lens and the focal length of the single lens is equals to capital F. The equivalent focal length of the combined lens is given by 1 by F equals to 1 by F1 plus 1 by F2. Remember that use the Sine conventions for the focal length of individual lenses, that is, if both are convex lens, then f1 and f2 both are positive. If both are concave lenses, f1 and f2 are taken as to be negative, and the first lens is convex, f1 is positive. If the second one is concave, f2 is negative. The final nature of the lens depends on the sign of f. If the sign of f is negative, that means the combination behaves like concave lens. If f have positive sign, then the combination behaves like concave lens. So this is the formula to find out the focal length of the combination of lens, that is equivalent focal length. Now we discuss about the power of the combination of two or more lenses which are in contact. As we know that the focal length of the combination of two lenses is 1 by f1 plus 1 by f2, where f1, f2 be the focal length of two individual lenses. Remember that the sign conventions on f1 and f2 once again. 1 upon f, we write it as power of combination. 1 upon f1, we write it as power of first lens, and 1 upon f2 written as power of second lens. So the power of the combination capital P, P1 plus P2. Here the final power of the lens P depends on its sign. If both lenses are convex, then P is positive, that is the combination behaves like a convex lens. If both are negative, P is also negative, the combination behaves like a concave lens. And if one is convex, other is concave, it depends again on the sign of P. Now we discuss a numerical. What is the power of combination of a convex lens and a concave lens of same focal length? The focal length of convex lens, say f, the focal length of concave lens is minus f. We know the combination power is P1 plus P2, that is 1 by f, 1 by f1 plus 1 by f2. P equals to 1 by f minus 1 by f, that is 0. That is, the power is 0. The power of any combination of lenses becomes 0. It indicates that the combination behaves like a plain glass sheet. Let us take one more example. Two thin lenses of power 2 diopter and minus 1.5 diopter are placed in contact with each other. Find power and focal length of the combination of lenses. Here the power of first lens is given as 2 diopter and the power of another lens minus 1.5 diopter. As we know the formula for the combination of power, the combination of the lenses having power is 0.5 diopter. Case B. What about the focal length of combination of lenses? The power of combination of lenses is equal to reciprocal of focal length of combination of lenses. So, f equals to 1 by p that is, the combination of lens behaves like a convex lens of focal length 2 meter. Why the convex lens? Because the equivalent focal length having positive sign, that is, the combination behaves like a convex lens whose focal length is 2 meter. Now we discuss one more numerical. There are two lenses. One is convex lens of focal length 50 centimeter and the other is concave lens of focal length 25 centimeter. We have to find out the power of combination of these two lenses. Here, first one is the convex lens of focal length 50 centimeter. Because it is convex lens, so the focal length is positive, and the another lens is concave, so its focal length is negative 25 centimeter. First we find out the power of these individual lenses. P1 equals to 100 divided by f1, that is 50, 2 diopter. Similarly, P2 equals to 100 by minus 25, that is minus 4 diopter. The power of combination is P1 plus P2, that is 2 minus 4, which is equals to minus 2 diopter. Here we get a negative sign, that is, the combination of these two lenses behaves like a concave lens of power 2 diopter. Thus, the combination behaves like a concave lens of power 2 diopter. Let us discuss the magnification of combination of two or more lenses. There are some lenses whose magnification produced is M1, M2, M3 and so on. The equivalent magnification produced by this combination is given by M, which is equal to the product of individual magnifications produced by the lenses. That is, M equals to M1 times M2 times M3 and so on. That is, if there are number of lenses are there and we have to find out the magnification of this combination, that is equals to the product of all the magnifications of individual lenses. This fact of the magnification produced by the combination is used in different cameras. In this experiment, we show that how we use a convex lens of short focal length as a magnifying lens. Take your notebook in which something is written here. If we take the lens in a position such that the printed letters are in between the focus and optical center of the lens, we observe that the image of these letters will become magnified. That's why we are using convex lens as a magnifying lens. I'll give you one more example, convex lens as a magnifying lens. Some of the palmists and watch repairers use the convex lens to magnify the small objects so they can see the lines or the very tiny parts of the watch very easily.